Hi everyone, my name is Willi Kepplinger. I'm a grad student at the University of Vienna. I work with Vertici. And oh yeah, before I start, I want to thank the organizers for giving me the opportunity to speak and you all, telling you about my stuff, especially since it's sort of, well, this entire niche of contact topology is not very well known. Yeah, okay, so what's my goal here? I'd like to introduce the intersection of Riemannian geometry and contact topology to you, some wider audience. So if you haven't heard about this before, which I guess is quite likely, then there's a good reason for that, which I think is that not so many people that do contact topology know Riemannian geometry. And so there's just, not a lot of people thinking about these kinds of problems. But I'd like to convince you that it may make sense to care about these sorts of problems, to care about these methods. And, maybe you can even find a problem that interests you. So yeah, let's try to get into it. I'm going to, right, so the first talk is going to offer some sort of background information and some motivation for why to even bother with all of this. And then in the second talk, I'm going to present some of my own ideas, and I'm going to tell you about some future directions, sort of some directions in which you yourself maybe even could do some research. Okay, so let me start with some general observations. The first is sort of the following. So in three-dimensional topology, we are sort of used to the idea that geometry is very powerful. This is sort of, not true in higher dimensions. Let me just, say that geometrization is an extremely like, powerful idea. And it's not completely unreasonable to hope that maybe geometry can help you out in other parts of three-dimensional topology as well. So let me put it like this. So geometry is powerful in dimensional 3. Now, here's a question. Can it be used in contact topology? Or in order to understand contact topology? More specifically, a big open question in contact topology is, well, in three-dimensional contact topology in particular, which three manifolds actually admit, tight contact structures? That is, the ones that people sort of actually care about. The ones that, have sort of a deep tie to the manifold itself. I mean, yeah, that help you understand submanifolds, that help you understand sort of relations to four-manifold topology. So, the tight context structures. So of course, for many three manifolds, it's known whether or not they admit tight context structures, but actually, for most, it's not. In particular, for hyperbolic closed three manifolds, it's unknown whether they support tight context structures. Again, in examples, it is known, but in general, it is not. And, hyperbolic ones, I'm sure you've heard the cliche, in some sense are most three manifolds, whatever you want to make of this statement. Yeah. All right, so open question. Do all hyperbolic three manifolds support tight context structures? Yeah, so this is wide open. People have no general clue sort of how to approach this question, as far as I'm aware. Well, but you can ask yourself, what do all hyperbolic closed three manifolds have in common? Well, they all have in common that they have a hyperbolic metric. And so maybe you can use this hyperbolic metric to say something, well, to give a partial answer to this big open question. That's the hope anyways. Now, here's a different sort of question that is also related with Riemannian geometry. Well, many people are interested in understanding the dynamics of Rayleigh vector fields. And now you can ask yourself whether there is a way of using Riemannian geometry to do something about the Rayleigh dynamics associated to a contact form. There's reason to believe this to be true. Okay, yeah, let me write something down. So give an alpha contact. Can we use Riemannian geometry to understand, to a certain extent, dynamics of the Rayleigh vector field of R alpha? Okay, I'm going to try to say something about all of these things. If you want to know more, I mean, there is only so much that's actually known, but if you want to know more, feel free to come to my office hours and we can have a chat. Okay, and another thing I want to mention is that throughout the talk, I'm going to highlight some connections to other fields and open questions. Yeah, so maybe, if you're a young and malleable grad student and you want to think about these sorts of questions, maybe you can use these to orient yourself. Okay, so let's, start the talk proper. So how do we use Riemannian geometry in order to say something about contact topology? It's a nice statement, it's a nice idea, but how do you do it in practice? Well, that's where the following definitions come into play. A contact form alpha, we need to couple the Riemannian geometry to the contact structure somehow. Yeah, one way of doing this is to pick a contact form and saying that a contact form alpha and the Riemannian metric G are called weakly compatible if, well, the Rayleigh vector field is orthogonal to the kernel of alpha, so to the contact structure, with respect to this metric. As you can probably imagine, this is far from unique. Well, okay, but let's still power through. This condition is actually equivalent to having a certain nice decomposition of your Riemannian metric, and it's also equivalent to your contact form solving some nice PDE. I'm going to say more about this in a second. Yeah, so this PDE, the thing I wrote down sort of looks like an eigenvalue problem, and indeed it is. And sort of this lambda on the right-hand side of this equation is something like the local instantaneous twisting of the contact structure with respect to this contact form, with respect to this Riemannian metric, and it doesn't actually depend on the contact form. Okay, and now we can sort of strengthen the compatibility by asking this, sort of local instantaneous twisting to be constant, not just some positive function, and by asking the Rayleigh vector field to have constant length. Okay, I mean, at this point, I guess you sort of have to accept this, but I'm going to tell you a cool fact, which is R alpha being orthogonal to psi and lambda being constant is equivalent to the contact form solving this eigenvalue problem, where again lambda is constant. Let me give this operator here a nicer name. This is called the Beltrami operator here. Okay, so you can sort of understand compatibility between a Riemannian metric and a contact form as the contact form solving a certain PDE that is defined in terms of the Riemannian metric. Yeah, let me just say that this Beltrami operator is sort of as nice as PDEs, well, as differential operators get. It's elliptic if you restrict to appropriate subspaces of your, smooth forms, whatever. It has compact resolvent. It satisfies some, its solutions. The solutions to this eigenvalue problem satisfy some unique continuation property. It's all very nice. Yes, I should have put this here somewhere. It's an operator that takes one forms and gives you back one forms. The exterior derivative takes you one form, gives you a two form, and the Hodge star in dimension 3 takes a two form and gives you one form. Okay, so this is a fantastically nice operator, but you may be wondering, well, okay, so what? Well, it turns out that every contact form alpha is a solution to this eigenvalue problem for some alpha and lambda. Okay, so that's pretty cool. And it sort of tells you that there is a geometric analysis sort of way of studying contact topology, at least sort of in principle. That doesn't, yet mean that this is a very fruitful approach to the subject, but I think it's pretty interesting. Now, what about the converse? So conversely, any solution to this eigenvalue problem is not necessarily going to give you a contact form, but it's going to give you something that's quite close to something that's a contact form. So it's going to any solution is going to satisfy alpha by G alpha greater equals 0. So that's an equal here, and it's equal to 0 at some point in our manifold M, exactly when alpha restricted to this point is just 0. Okay, so in the complement of the 0 set, this gives you a contact form, and sort of this operator being as nice as it is means that the 0 set is very small. In particular, if you choose a generic Riemannian metric G, then the 0 set is going to be finitely many isolated points in your closed three-manifold. Okay, and I just want to mention at this point that studying these singular solutions, I think, is sort of very interesting. Maybe I will talk about this in the second part of this talk. Another remark that I find sort of interesting is that this Beltrami operator pops up in a number of questions that are not necessarily related to contact topology. Well, at least, a priori. I mean, since this operator pops up, it's actually related to contact topology. But yeah, so other people care about this. For example, the square of this Beltrami operator is just the Hodge-Laplacian on one forms restricted to an appropriate subspace. The lowest eigenvalue of this operator is sort of related to L-spaceness, funnily enough, due to, well, that's a fantastic result by Francesco Lin and Lipnowski. Yeah, more specifically, if you have a rational homology sphere that is hyperbolic, then you can look at the lowest eigenvalue of this operator in absolute terms with respect to this hyperbolic metric. And now, if this, well, sometimes all right. Analyzing this lowest eigenvalue can tell you whether or not this hyperbolic rational homology sphere is an L-space sometimes. So it gives you a sufficient condition for that, which I think is very cool. And another thing that is true is that the eigenforms of this operator, of this Beltrami operator, happen to be stationary solutions of Euler's equations. So there's a certain subset of the community of people doing fluid dynamics that care about this operator for precisely this reason. And there's sort of a fruitful interaction between contact topology and fluid dynamics here, which I think is very funny, and more people should know about this. Okay, now let me briefly outline an open question here. If you take an isotopy class of contact structures, then you can sort of look at the space of metrics that are compatible with some representative of this isotopy class. And now it would be interesting to know what the topology of this space is. If you can show that topology is non-trivial, remember, by the way, that the space of all Riemannian metrics on a manifold has trivial topology. It's even convex. It's contractible to a point. But if you can show that sort of the space of compatible Riemannian metrics, compatible with some isotopy class of contact structures, is non-trivial, then you would have proven something that people just approaching, say, Euler's equations analytically would never have been able to show. That would be very cool. So, if you want to know more about this, come talk to me in the office hours. Okay, so now I've just barely told you the definition of what it means for a Riemannian metric and the contact structure or form to play nicely with one another. Yeah, let me, tell you about some actual results here. So, the idea of this entire compatibility thing is, suppose that you have some contact form and the Riemannian metric that are in some sense compatible enough. So there is some measure of compatibility here, and suppose this is good enough, and suppose that the Riemannian metric has nice curvature properties, then this implies that the kernel of alpha is tight. That's a very vague statement, but let me give you an example. So if alpha and G are compatible, and the sectional curvatures, so some measure of curvature of Riemannian metrics is 1/4 pinched, which more or less means that in some sense the curvature is homogeneous. Then this implies that the kernel of alpha is tight. So that's the celebrated sphere theorem proven by Etnayer, Massot, and Komendachik. Yes, and there's several other sort of criteria that I won't bore you with. It's not just sectional curvature. There's a bunch of those by now. And the idea sort of is that again, that you have this compatible pair that sort of tells you that the Riemannian metric knows something about the context form. And now if the metric is very nice, hopefully the topology of the kernel of alpha is also nice. Right. So here's a question. All of these criteria, all the criteria that exist for now are tightness criteria. So they are sufficient criteria to show tightness, but there are no known criteria that imply over-twistedness. And if you can find any such criterion, I can assure you that people would care about this. But I think it's not that easy. Otherwise, I would have done it already. Okay. Now, why do we care? Once again, so one hope is that one can use this criteria to prove the existence of tight contact structures on hyperbolic three manifolds. So how would you do this? This is just a rough outline of a sort of proof strategy. But what you could try to do is, well, you take your three manifold, you take a hyperbolic metric, and now you solve this eigenvalue problem, and hopefully get non-singular solution, non-singular alpha. So an honest contact form. Now, since alpha solves this equation, this means that G and alpha are weakly compatible. And it just so happens that, the hyperbolic metric is a very nice metric in a sense. So the idea now is that we just hope that they are compatible enough. So hope they are compatible enough to imply tightness of the kernel of alpha. Now, this is very vague this is sort of vague. But in particular, it's true that, there's something called the Bochner formula, which in this negative curvature setting gives you an upper bound on the total twisting of the context structure, whatever exactly that means. But now if someone can show that there's also sort of an upper bound on the local twisting, then I could prove that this means that hyperbolic manifolds with small lowest eigenvalue of this operator have tight context structures. At least provided I can also show that there exists, that the associated solution is non-singular. But I sort of suspect this would follow from the fact that it has little local twisting. Well, whatever. This is a difficult question in harmonic analysis. The experts in harmonic analysis don't know how to do this. But what maybe you should take away from this is that if people make progress, this particular sort of progress in harmonic analysis, then this would have implications for contact topology. I think this is very cool. I'm not sure you knew about these two fields sort of having this kind of connection before, and yeah, I hope you enjoy it as much as I do. Okay, then let me tell you about something else real quick. The connection to rape dynamics. So I'm just going to give you one example here. There's a lot of people that care about the rape dynamics that arise from taking a convex domain in R4, let's say, with the standard symplectic structure, and now you do your thing. You take this convex domain, you sort of center it in R4. You take the radial vector field, which is Liouville, and this gives you a primitive of your symplectic form, and now you restrict the resulting one form onto the boundary of this convex domain. This gives you a contact form. But yeah, and now there's sort of some big conjectures around regarding the rape dynamics of contact forms that arise in this way. But the problem here is that convexity is not a symplectic notion. You can do symplectomorphisms to your convex domain, and they're no longer convex. So in a way, it's sort of not. Convexity is not a notion that is in the symplectic vocabulary. However, it is a notion that is connected to the Riemannian geometry of R4. And so some people are thinking that maybe you can use Riemannian geometry here to sort of give you a feeling for, if someone gives you the boundary 3 manifold abstractly, it gives you a contact form there. Maybe Riemannian geometry gives you a way of seeing whether or not a form arises as this sort of filling, as sort of the boundary of this convex domain in R4. Yeah, so let me briefly tell you something about this. So suppose that we have some hypersurface in R4. Then and suppose it's the boundary of a convex domain. Now, if the Liouville vector field is orthogonal to the boundary of this domain, to M, then it turns out that the restriction of the metric and the restriction of this primitive of the symplectic form, so of this Liouville 1 form, are weakly compatible. Now you may wonder, are there any interesting domains for which this condition is satisfied? Yes. For example, the convex toric domains. If you don't know what it is, don't worry about it, but the fact is there's sort of an interesting class of examples of this happening. And yes, and I think there's sort of something that can be said. At least, I think you can find necessary conditions that somehow you can find properties that these contact forms have to satisfy that you can formulate in terms of Riemannian geometry. Okay, so this more or less ends talk 1. So I hope I managed to convince you to also attend the second part, in which I will talk about some of my own ideas. Yeah, so thank you very much, and hopefully see you soon.